We derived these equations last time, and now at this point Einstein states that we should compare these equations in vacuum. Remember that we made our considerations here in vacuum, so only considering gravitational energy and not energy pertaining to matter. So we should compare these equations with the corresponding equation in classical mechanics, and Einstein states that the equation should be del squared phi equal to 0, which is Poisson equation in the absence of matter, because with the presence of matter, this equation is written like this: del squared phi equal to 4 pi k times rho. Rho is the density of matter, whereas k is the constant that we usually call g in physics, the gravitational constant. Einstein calls it k. Therefore, Einstein argues that in the general theory of relativity, we must introduce a corresponding energy tensor of matter, T alpha sigma, capital T in this case, whereas in here we have lowercase t, and this tensor T alpha sigma should be symmetrical. So T alpha beta written like this should be symmetrical, or T alpha beta written like this with upper indices should be symmetrical. And this can be expressed by introducing in this equation here this kind of tensor. So in place of T sigma mu here, Einstein states that we should put uppercase T sigma mu plus lowercase T sigma mu, because lowercase T sigma mu considers only gravity, as I said, whereas capital T sigma mu considers matter, because T sigma mu, lowercase T sigma mu, represents the energy components of the gravitational field alone, and we have to replace lowercase T sigma mu with the total energy, which is given by the joint action of matter and gravity. So the equations will become like this: d over dx alpha of g sigma beta gamma alpha mu beta equal to minus k, and here we have T sigma mu, lowercase T sigma mu, plus capital T sigma mu minus 1/2 delta sigma mu T lowercase t plus uppercase t, where t is defined as T mu mu, and this is called Laura's scalar. Let me write it down. It's spelled like this: Laue, and it's called Laura's scalar. And this equation here can also be written like this: derivative with respect to x alpha gamma alpha mu nu plus gamma alpha mu beta times gamma beta nu alpha equal to minus k uppercase T mu nu minus 1/2 g mu nu times capital T. And this term here on the right is equal to 0 if there is no matter. So we get back the field equations in vacuum written in one of the forms that we have previously encountered. Because remember that in vacuum, this term here is indeed equal to 0. We also derived it from a variational principle. And remember that the condition that the square root of minus g should be 1 is still valid. Now let's consider the laws of conservation in the general case. We have to ascertain that the law of conservation is satisfied also in the general case. Let's construct the indices sigma and mu in this equation here. Let me zoom out. In this equation here, we are going to contract the indices sigma and mu. And what we obtain is this. So contract the indices and multiply also by this tensor, 1 over 2 delta sigma mu. If we contract the indices, we get d over dx alpha times g lambda beta gamma alpha lambda beta equal to 1/2 k delta sigma mu t plus t. Now, by putting the two equations together, this one here and this one here, and by putting them together, I mean you have to subtract this one from this one. So if we do that, we get derivative with respect to x alpha of g sigma beta gamma alpha mu beta minus 1/2 delta sigma mu times g lambda beta times gamma alpha lambda beta equal to minus k t sigma mu plus t sigma mu. Now let's take the derivative of this expression with respect to x sigma, and the first term here can be written like this: d squared with respect to x sigma x alpha of g sigma beta times gamma alpha mu beta, and this is equal to, if we insert the expression for gamma alpha mu beta, minus 1/2 d squared with respect to x sigma with respect to x alpha of g sigma beta times g alpha lambda times derivative of g mu lambda with respect to x beta plus derivative of g beta lambda with respect to x mu minus derivative of g mu beta with respect to x lambda, and it's quite easy to see that if you consider these two terms, this one and this one, they will cancel. If you check the expression and relabel the indices appropriately, and therefore what you get is this. This is equal to, you have 1/2 d squared over dx sigma dx alpha of minus g sigma beta g alpha lambda derivative of g beta lambda with respect to x mu. And this, according to some previous rules that we have found in tensor calculus, is equal to the derivative of g with upper indices sigma alpha with respect to x mu. Therefore, this is equal to 1/2 d cubed g sigma alpha with respect to x alpha, x sigma, and x mu. Now, we have to consider the derivative with respect to sigma of the second term here. Remember that we also have this operator, d over dx alpha. So let's write it down here. We have minus 1/2 d squared over dx alpha dx mu times g lambda beta gamma alpha lambda beta, and this is equal to, if we insert the expression for gamma, 1 over 4 d squared with respect to x alpha dx mu. We have g lambda beta, g alpha delta, and this multiplies dg delta lambda with respect to x beta plus dg delta beta with respect to x lambda minus derivative of g lambda beta with respect to delta. Let me close the brackets here, here, and here, and this is equal to, now you can also check, then when we multiply this by this, we know that this term, when multiplied together, is equal to 2 over the square root of minus g times derivative of square root of minus g with respect to x delta. But since the square root of minus g is equal to 1, in our case, this is equal to 0. And also we can combine these two terms together when we multiply, and this will be equal to 1/2 second derivative with respect to x alpha with respect to x mu of g lambda beta g alpha delta derivative of g delta lambda with respect to x beta. And this term inside the square brackets is equal to minus the derivative of g alpha beta with upper indices with respect to x beta. And therefore we get minus 1/2 d cubed g alpha beta with respect to x alpha x mu and also with respect to x beta. Now you see that this term here is equal to minus this term here. So this term and this term will cancel. So we found that d squared with respect to x alpha and x sigma of g sigma beta gamma alpha mu beta minus 1/2 delta sigma mu times g lambda beta times gamma alpha lambda beta is equal to 0. So the derivative with respect to sigma of the left hand side of this expression is equal to 0, and therefore we also get that the same derivative of the right hand side should be equal to 0. So all in all, we get d over dx sigma of t sigma mu plus t sigma mu, in this case with the capital letter T, equal to 0, which is the law of conservation. So this is very important in the theory of general relativity, and it's why Einstein took the time to derive this expression because it had to be derived from his theory in order for the theory to be consistent and contain classical mechanics. Now let's make other considerations regarding the field equations. Let's see what other implications are of this theory of general relativity. Let's start with these equations here. Derivative with respect to x alpha, gamma alpha mu nu plus gamma alpha mu beta times gamma beta nu alpha equal to minus k t mu nu minus 1/2 g mu nu times t. And of course the square root of g is equal to 1. We have already written this equation earlier, but now let's consider multiplying this first equation by the derivative of g mu nu with respect to x sigma. Now notice that when we multiply both sides of this equation, especially this term here, we will have g mu nu, which multiplies this derivative g mu nu with respect to x sigma. But this term here multiplied by this derivative will be proportional to the derivative of the square root of minus g with respect to x sigma. And of course, this will give 0, since the square root of minus g is equal to 1, therefore it is a constant. So this will give 0, and when we multiply by this term, we can avoid considering this term because it will give 0 contribution. So here we get d g mu nu with respect to x sigma, and remember that in previous lectures we rewrote this term as, by definition, g mu nu sigma, written like this. Then this multiplies derivative with respect to x alpha of gamma alpha mu nu. Then here we have plus gamma alpha mu beta times gamma beta nu alpha, and this is equal to minus k derivative of g mu nu with respect to x sigma times t mu nu. Now, in one of the previous lectures where I considered the variational principle, this term here, we derived it to be equal to minus the derivative of some function h with respect to g mu nu with upper indices here. Whereas this term here, gamma alpha mu nu, was equal to the derivative of the same h, the same function h, with respect to g mu nu alpha. And remember that the function h was defined to be g mu nu gamma alpha mu beta times gamma beta nu alpha. So what we really have is this g mu nu sigma times derivative with respect to x alpha of derivative of h with respect to g mu nu alpha minus derivative of h with respect to g mu nu equal to minus k derivative of g mu nu with respect to x sigma times t mu nu. We have already dealt with this expression on the left, but let's do the same steps that we did in that lecture regarding the variational principle also in here. So the first term here in particular can be rewritten like this. We have g mu nu sigma derivative with respect to x alpha dh with respect to g mu nu alpha. This is equal to the derivative with respect to x alpha of g mu nu sigma times derivative of h with respect to g mu nu alpha minus derivative of g mu nu sigma with respect to x alpha times derivative of h with respect to g mu nu alpha. Now this term here is equal to derivative of g mu nu alpha with respect to x sigma, because the order of derivatives is not important. So if we exchange the order, we can also exchange the order of the two indices alpha and sigma. So on the left hand side, we will have derivative with respect to x alpha of g mu nu sigma times derivative of h with respect to g mu nu alpha. And if you combine the other terms, you get minus derivative of h with respect to x sigma. And this can also be written like this, derivative with respect to x alpha of g mu nu sigma times dh with respect to g mu nu alpha. And then here we have minus delta alpha sigma times h, like this. And we had already defined this quantity here as minus 2k times lowercase t alpha sigma. Therefore, what we get is this. We get that the derivative of lowercase t alpha sigma with respect to x alpha is equal to 1/2 derivative g mu nu with respect to x sigma times uppercase t mu nu. But now, since we also know that this equation must be satisfied, and let me write it down, derivative with respect to x alpha of lowercase t alpha sigma plus uppercase t alpha sigma is equal to 0. If we combine these two equations together, we can write derivative t alpha sigma with respect to x alpha plus 1/2 derivative of g mu nu with respect to x sigma times t mu nu uppercase t mu nu equal to 0. And this equation here should remind us of something that we have written in previous lectures. In particular, we had derived this formula. So let me write down the formula that I have already derived in previous lectures. The equation was this: square root of minus g times a mu nu equal to derivative with respect to x sigma of square root of minus g a sigma mu plus 1/2 derivative of g rho sigma with respect to x mu times square root of minus g times a rho sigma. And this a mu here on the left is none other than the covariant derivative of the mixed tensor a nu mu. So this is Einstein notation, and in general relativity we usually denote that like this: delta nu a nu mu. So this is like a definition. This term is usually the covariant derivative of the mixed tensor a nu mu. But now, if we apply this formula to our special case, we know that the square root of minus g is just 1. This term here is 1. Therefore, you can see that this left-hand side of the equation here is none other than the covariant derivative delta nu t nu mu equal to 0. Namely, the covariant divergence of the energy tensor related to matter vanishes. This is what this equation tells us. And we saw also that this equation here can also be written in this form: square root of minus g a mu equal to derivative with respect to x sigma of square root of minus g A sigma mu plus gamma tau sigma mu times square root of minus g a sigma tau. And in our case, this equation here implies that this formula can also be written in this form. Derivative of t alpha sigma with respect to x alpha is equal to minus gamma beta alpha sigma times t alpha beta, like this. And this term here on the right expresses the energetic effect of the gravitational field on matter. And these four equations, they are four because remember the sigma can take the values 1, 2, 3, and 4. These four equations govern the dynamics of material phenomena. And this is where Einstein draws to a close for this section.